Welcome back to Applied Mathematics. In this video, I want to talk about similar triangles. The idea of similar triangles is one of the most important ideas in geometry and applications of it. There are two rules. The first one is very simple. It helps if I am using a normal size pen. When two triangles are similar, the lengths of corresponding sides are in proportion. So let's just consider a couple of triangles. All right. Here I have triangle ABC. And here I have triangle XYZ. And I am told in this situation that triangle ABC, I don't remember if I talked about that in the previous video or not. Triangle ABC, I literally draw a triangle to say I'm talking about a triangle. Similar is a tilde. Triangle ABC is similar to triangle ZXY. And you might be surprised at first that I've called this triangle ZXY instead of triangle XYZ. And the reason for that is that the naming convention is important. Remember, the lengths of corresponding sides of the triangles are in proportion. The way that we name our similar triangles tells us which sides are corresponding. Side AB corresponds to side ZX. And when you look at the triangles, you can kind of see that, yeah, those are probably the ones that match up. Right? Take triangle XYZ and kind of rotate it in your brain 180 degrees. Rotate it around so that it's twisted around from its current orientation, and you'll start to see what I'm talking about with that. Right. But let's continue on here. Let's invent a particular problem. Let's say that triangle ABC is our known piece of information. Triangle ABC has sides of length 12 feet, 8 feet, and 7 feet. And we have scaled up triangle XYZ so that side YZ over here is 25 feet. And I want to know what side XY is going to be. I can solve this problem by setting up the proportion and solving from there. I know it's going to be a proportion, and I know a proportion means I have some fraction equal to some other fraction. As you get comfortable working with similar triangles, you will find that you generally want to just dive in and start putting numbers in your proportion, but I encourage you to start off by using the names of the sides. It will help you develop this strategy of how to write the proportion. I also want to take a moment now and make sure that everyone knows that there are 8 different ways of writing a true proportion that will solve this problem. The issue is that there's also 24 different ways of writing a proportion that looks like it belongs in this triangle, but either cannot solve the problem or will give you an incorrect answer. So even though you have some freedom and you have some flexibility, you do have to be careful and make sure that you are writing the proportion correctly. So my guideline in working with proportions, working with similar triangles, is I always start with the unknown, xy. Then I look at the naming of the similar triangles, and I see that xy is the second and third letter in the name of the triangle. So I go to the other triangle, and I take the second and the third letter, and I say that xy corresponds to BC. Then I look to see what other kinds of information I have. Usually, you are going to be restricted on one or the other of the triangles in what you know. In this particular case, I have side xz down here that I do not know and I'm also not asked for. So I know that the only way I'm going to be able to set anything up is in the triangle with xy, I have to use yz as the other side. And same thing, yz is the first and last letter of the side in that triangle. So I'll go to the first and last letter of the side in this triangle, which is going to be CA or AC. Right? CA and AC are the same thing. They're talking about the same triangle, so it doesn't matter which way you put it in. Now I know that I have set up my triangle or my proportion so that it matches the triangle and it has the information that I am looking for and everything else known. I will substitute in, I'll call side length xy little x just so I have a nice comfortable variable to work with. Side yz was 25.0 feet. Side BC is 7.0 feet, and side AC is 8.0 feet. In this particular example, everything is measured in feet, and everything is going to be measured in feet, so I know the result is in feet. I don't have to carry that along with me. But I want to point out that if I modify this problem just a little bit, and I call all of these measurements on this triangle measurements in inches, while I leave the other triangle in feet, it doesn't actually change anything at all about what I've just done. Right? This measurement is in feet. If this measurement, the unknown x, is also in feet, then the units will cancel out between numerator and denominator. This measurement is in inches. This measurement is in inches. The inches cancel out in numerator and denominator. I know that x has to be in feet, and then all the units cancel out, and my equation is unitless from here. But from here, it's just a matter of solving the proportion. Using the cross product test, I get 8.0 times x is equal to 7.0 times 25.0. 7.0 times 25.0 is something 175, but I only have two significant digits, so I'll round that and call it 180. And then divide that out, I get 22.5, but again, only two significant digits, so I'll round that and call it 23. And I said at the start of this that x had to be in feet for the units to work out. So I get around 23 feet. If you had rounded differently as you went through this, you might have gotten 22 feet instead. That's really no different. Remember, the significant digits convention tells us that the measurement of 22 feet and the measurement of 23 feet are of negligible difference. there's an overlap where there's about a 50% chance that they're the same measurement anyway. All right. So that's all well and good. But I guess the interesting question that remains is, how do we know when a triangle or when two triangles are similar? Two triangles must be similar if all three pairs of corresponding angles have equal measure. Here's the phrase corresponding angles again. We talked about that when we talked about parallel lines, and the meaning is different here. But at the same time, it's the same meaning. You just have to be a little bit more abstract about what you mean by the same. The picture of each of the triangles has three angles. And if you rotate, stretch, and flip around the triangles so that they line up with each other, the angles that line up are the corresponding angles. If those angles have the same measure, the triangles are similar, and you can continue with that rule of side lengths in proportion. Although we can actually do a little bit better than that. We know that the three angles of a triangle add up to 180 degrees. So if you get one pair of corresponding angles that have equal measure, and you get a second pair of corresponding angles that have equal measure, once two angles of the triangle are known, the third one is determined. Just take 180 and subtract the measures of those two angles. And so if the two angles are the same, the third angles must be the same as well. We can simplify this requirement. Two triangles must be similar if at least two pairs of corresponding angles have equal measure. All right. So with that in mind, let's draw a picture. This figure is sometimes referred to as a bow tie figure. I have no idea why people think it's one of my favorite figures, but there we have it. All right, in the bow tie figure, let's go ahead and name a couple of points, A, B, C, D, and E. We're going to be given that AB is parallel to DE. We're also going to be given a couple of side lengths. And I'm listing them out instead of putting them on the figure because, well, quite honestly, I don't have enough space on the figure. But we have two parallel lines. We have a couple of known side lengths. I'm going to go ahead and highlight our known side lengths. We know this side. We know this line segment. We know this line segment. We know this line segment. And we are asked for this line segment. Before we can get there, we do have to establish, are there similar triangles? Do we know we can set up a proportion? And as I said on the previous example, once you get comfortable with this, as you start to really understand what you are doing, you're going to find that you less and less need to write everything out. But in the meantime, as you are starting to get the habit here, as you're starting to get the structure of this, writing out everything in detail will help you make sure that you get your corresponding things to actually correspond. And that starts with the work of the corresponding angles. So, in this figure, we have corresponding angles. I think that the most obvious one is at point C here. I'll go ahead and write out the explanation. I don't necessarily need that from you, but the angles at C are vertical. They have equal measure. Then I have two parallel lines which are cut by a transversal. Because of that, this angle and that angle are alternate interior angles. They are angles that will have the same measure because of parallel lines cut by a transversal. So angle A and angle E are alternate interior angles. You could from here also say that angle B and angle D are alternate interior angles, but you don't need to because we've now established everything we need to establish. From here, we can start talking about the figures, similar triangles. I have two triangles. The first one I can name however I would like. So I'm going to name it in alphabetical order and call it triangle ABC. That's going to be similar to another triangle. All right. A corresponds to E. B we didn't mention. That corresponds to the other angle we didn't mention, in this case D, and C corresponds to C. EDC definitely describes the triangle that I'm trying to place over here as being similar. With that information in mind, we can start naming our proportion. DE is the side that we are interested in. I always start with the side we're interested in. That way I'm sure I don't forget it. The triangle that has DE also has a known side CD. Since that's the only other known side of the triangle, I had better include that as well. All right, we have that third side of that triangle that we don't know anything about and we also don't care about. So I'm making sure that it doesn't need to be included. Then I'm using my similar triangle statement to figure out the other half of the proportion. DE or ED, right? The order of the letters doesn't matter. It's the first two letters over here. So we take the first two letters over there. DE corresponds to AB. Then I have CD, or again, DC. The order doesn't matter as long as it's the same two letters. It's the last two letters over here, so it must be the last two letters over here, BC. With that information in hand, DE is my unknown. I'll write a little x for that. CD on this list is 3.75. AB is 12.5. BC is 16.0. All of these measurements are in inches, so I know that my resulting value is going to be in inches as well. I don't have to carry inches along with me throughout the entire process. All right, but cross product test 16.0 times x is equal to 3.75 times 12.5. My calculator is happy to tell me that 3.75 times 12.5 is 46.875, but I only have 3 significant digits. So let's go ahead and call that 46.9. And then get x by itself by dividing by 16. And getting something in the ballpark of 2.93. Again, if you're off a little bit, we'll call that rounding error. Right? You might have gotten 2.92 or 2.94. That's not a big deal. But in any event, that's all there is to it. Right? So we can look at a situation, we can recognize that there are triangles. We can use properties of angles to determine if the triangles are similar. Once we know the triangles are similar, we can use that to write a proportion. We can solve the proportion to find the length of an unknown side. Next time I'm going to look at a couple of practical applications, how we can use this to our advantage in everyday life. Well, maybe not quite everyday life, but often enough in the real world. For now, though, that's all I have. So as always, thank you for joining me. I'll see you next time.